Yeah. Okay, and then let me just check one more thing. Okay, Liwei, are you ready?
Yes, yes.
Very good. Then welcome back, everyone, to our morning session. Our next speaker is Liwei Ji. He will be online. So if you do have any questions, please raise your hand. I will be checking here in the room. Also, for those of you who are online, I'm logged in. So if you have any questions, either post it in the chat or raise your hand. I'm monitoring that as well. And then without further ado, Liwei, he will talk about GPU-accelerated subcycling time integration with the Einstein Toolkit. So please take it away.
Okay, thank you. Hi, everyone. I'm Liwei. I'm a postdoc at IIT. Yes, please stop me in the middle if you have any questions or comments, because you will help me fill in the 1 hour slot of this section. Yeah, today I'm going to talk about subcycling implementation in CarpetX, and it will be two parts. The first, I will describe the implementation of the subcycling in CarpetX, and also the tests. And the second part will be introduction how to modify your CarpetX SOMs to use the subcycling implementation. So before we go to subcycling, I would talk a little bit more about CarpetX. It's a new driver for Cactus, and it's based on MREX, and it has the following new features. First, it supports the stacked grid function natively, and it has very good performance portabilities. It supports parallelization through MPI, OpenMP, and also the hybrid OpenMP, MPI, OpenMP, and also MPI GPUs. The next feature is that it supports the adaptive mesh refinement, fully adaptive mesh refinement, if you will. And it also have very efficient I/O, which support the OpenPMD and the silo format, and also have output in the ASCII format. Another feature is it has some safety checks that can prevent the user to do some not intention grid function operations. And it is available here. And based on this new driver, there are a bunch of new songs which already can use these drivers. So here are two examples. So for the spacetime evolution, we already have a spacetime X, which contain all the components which can be used to do vacuum simulations. And for the GRMHD simulations, we have AstroX, which are available here. And Jay will talk about this in next. Okay, before we go to the subcycling implementation, I want to talk a little bit about the difference between two typical AMR strategies, so-called patch-based and arc-tree-based AMR. So for the patch-based AMR, it has the proper nesting of refined grades, which means that the fine grade will always sit inside a coarser grade, and and it will have multiple copy of the same function at the same point on different levels, and because of this nesting structure. And for the arc-tree-based AMR, you don't have overlapping between different levels of refinement. And if you look at any specific position of the grid, you will only have one copy of data. And the next difference is that for the patch-based AMR, the data you have is distributed level by level. So for example, that we distribute the courses level to all the computation node you have. Then after that, you go to the next level and distribute this level to the to again the same all the all the computation node you have. And well, for the octree-based AMR, that you will distribute all the grid data you have to all the computational node you have. And because of this difference in the data distribution between these two AMR formulation, it's I would say then if you think about it, then when you do the evolution, say you evolve a time step for all the levels, then because you for the patch-based AMR, because you distribute data level by level, then you will have to evolve the data level by level. But for the octree-based, and then you can evolve all the levels at the same time. So if you are taking uniform time step for both of these two methods, then the patch-based will take the number of levels more times to evolve to the same a same time step compared to the octree-based. So this is very bad. So what can we do to improve the patch-based AMR? So because of this specific data distribution method, it's quite natural actually to implement subcycling with the patch-based AMR compared to the octree-based AMR. So here I want to talk about the subcycling. By subcycling, what do I mean by subcycling? So here is a plot. So the x-axis will be the spatial direction, and the y-axis will be the time direction. And I'm using the thickness of the line to represent the resolution of the levels. So as you can see on both sides, we have 3 levels of refinement. And first we have courses level, we have a second course level, and we have a finance level. So by subcycling, so the most simple way, we just evolve all the levels using the same time step. That will be the most simple way to. But because of the CFO condition, we can actually using larger time steps for the course level and the smaller time step for the fund level. And if we are using uniform time stepping, then the time step will be limited by the finance level. So the left will be subcycling in time, the right will be the non-subcycling uniform time, uniform subcycling in time. So because that the different data distribution strategy, and it's more natural to using subcycling in the octree, the patch-based AMR. Here we only compare the patch-based AMR plus subcycling and to the octree-based AMR without subcycling. Then if you and here we suppose that you have infinite computational resources. You can have as much computational knowledge as you want, and there's no cost in the communication. Then we can say that for these arrows, so for the subcycle, let me remind you of subcycling, what's really happening in the subcycling case. So first we evolve the courses level. Then after that, we take another step for the second course level. Then they wait. Then again for the even final level, and after that you take another final level. Then after the second coarser level and the finest level matches, we evolve the second coarse level again and evolve the final again until they all matches to they all go matches to the complete 10 step. That's the subcycling algorithm. So again, assuming that we have infinite computational resources and there's no cost between the communication, then you can compare this time. Then we will have the same. Oh, excuse me. We will have. It will cost the same more time to make a arrow, to make a time step, the same arrow. So if you count the number of arrows here, for the subcycling case, you will have actually almost 2 times. So this is 7 compared to 4. So you will need almost 2 times the wall time to make the for all the levels to evolve to the same time step compared to the non-subcycling case. But this is only one aspect of this comparison, that if we count the wall time, that the non-subcycling actually wins, non-subcycling with oxygen wins. But if you can also count the actual cost of the resources, basically how many zone cycles it needed to make this complete time step. So so here I brought the comparison between these two methods again. That this is the wall time comparison between the octree and the patches. So as you can see, if they all have only one level refinement, then they will be the same. But if you go to multiple levels of refinement, then the wall time it takes for the patch-based AMR will be 2 times slower compared to octree-based AMR. But if you are counting the computational resources that needed to, or in our zone cycles to make the same time step for both methods, then the octree-based will cost much more resources compared to the patched-based AMR. So without subcycling, we will cost the same resources, and will be 2 times slower compared to octree-based. No, actually, not only they will cost the same resources and much slower compared to the octree-based AMR, but with subcycling, even though we can still only have maximum half the speed of the octree-based AMR, but we can save a lot of computational resources by using the patch-based AMR. So subcycling is quite essential to such that the patch-based AMR actually at least comparable to the octree-based AMR. So we spend. That's the reason. Yes.
Before you continue, can you go back? I think Roland has a question. And Roland, can you just speak up, please?
Yes. So you might have said that, but when you talk about the time and that you're spending, and you find that the octree one is faster, does that mean you're running on very, very many compute nodes, or?
Exactly. That's basically has reflection. It will reflect on the some cycles. Yes, you will use much more computation node to achieve this faster. It's 2 times faster compared to patch-based. Yes.
Okay, interesting. So the overall scaling is good enough that you can basically scale your way out of being slow on the octree without a subcycling. Interesting.
Sorry, say again?
So the performance improvement is the overhead that you have with the patch-based system is large enough that with an octree one you can scale your way out of being slower. even though you don't have subcycling in time. Interesting.
Yes, yes.
And that's true for many levels of mesh refinement, apparently. I would have thought that eventually this goes away. But once you have 13 levels, I would have thought you just spend 4,000 times the time to do the finest time step.
No, if you have a lot of level refinement, you will need much more computational node to maintain the same speed for the finest level, right? For the tree.
Right, eventually you should run out of grid points to distribute them across your nodes. Unless your domain is
exactly.
gigantic.
Yes. Okay.
Okay,
Should
very
I?
good.
Thank you.
Are there any other questions? I don't see anyone in the room. Online, anyone else? No? Then please continue, Liwei.
Okay, thanks. So, okay, then I will talk about how did we implement the subcycling inside with the new driver CarpetX. So that's here's the description of the RK4 method. So consider that you have ODE and you have initial data Y0. Then in order to update to the next time step, then first you will prepare some intermediate stages. Here we call this intermediate stages capital Y1, capital Y2, capital Y3, and capital Y4. And with this intermediate stages, then you can calculate the intermediate speed of K1, K2, K3, K4. Then with this intermediate speed, then you can construct the value of the function at next next time step. Okay, so let me talk about the old subcycling algorithm which exists in the CarpetX driver. Here, again, the y-axis will be the time direction, and the axis will be the spatial direction, and this black point will be the boundary between the courses level and the fine level. So basically, left will be the coarser level, and the right will be final level. And so first we evolve the coarse level to the next time step, and for the fine level, we'll need 2 sub-steps in order to match the coarse level. And here we're also using another 3 lines to represent the intermediate stages of the RK4 method for the first and the second sub-step. Yes, so in order to fill in the boundary point of the mesh refinement, so in Carpet, what we do is we add the so-called buffer point. So for the RK4 method, we will need 4 times of the ghost point you use in your simulation. So here, each circles represent the size of the ghost point that you choose for your simulation. And basically, we have four times of that ghost size. And so at the beginning, at this step, first we evolve the coarse level. Then in order to evolve the fine level, first we do a prolongation from coarse to fine to fill in these circles at the initial time step. And because when we evaluate the case from the intermediate stage of capital Y's, there will be finite difference operate, then which will after you so this is the first intermediate stage, and you evaluate it to get a case, then the first boundary point will be invalid because the finite difference operates. So you will only left with three circles which is valid. Then you continue, and you can continue to evaluate K2 Y2K2 and Y3K3, and in the end, you will only have valid K4 for the boundary point of the fine level. So, but here we only evolve the first sub-step for the fine level. So we also need to evolve the next sub-step. So what we do is using time interpolation, using the coarse level for the previous and the next step, and also even previous, to interpret in time to fill in this blue point, and also there will be a prolongation, to fill in the blue point. Then we can using the same pattern to get the K4 for the boundary point of the final level. Then we have all the information we need to actually get the function value at this time slice. But as you can see, that in order to evolve to do subcycling in time in Carpet, we actually introduce 4 times of the ghost zones at a refined boundary, and it can be really expensive. And we also keep evolving this buffer zone. There will also actual calculation required. So after we have this wise, we do restriction from this fine level and to the coarse level, which share the same physical domain of the coarse level. So can we do better by instead of adding so many buffer points? So the answer is yes. So instead of using buffer zone, we can do so for basic. We need the intermediate stages at this point in order to fill in to get the case for the boundary point. So there's actually we can do a Taylor expansion of the intermediate stages around the time direction, and here's the expression. Then if we can fill in the y's, then we can somehow prepare this y's not using buffer zone. We can still we can still using the subcycling without using the buffer zone point. So so here's the Taylor expansion of the capital Y's, and now we represent this Y's with the initial value of the function, and also the time derivative of this function. And so the next question will be, how can we prepare this this small y and the y prime, or time derivative of these y's? So there's actually so the answer is the dense output. So then let me explain a little bit about this dense output. So what this says is basically that if you already evolve, take a RK4 step, complete RK4 step, then with the case, intermediate speed case, then you can construct a polynomial such that you can, here the theta will be 0 and 1, which will parameterize the distance between the initial the yn and the yn plus 1, basically. So you can have a polynomial that you can evaluate anywhere between the yn and the yn plus 1, and it's accurate. It will have the same accuracy for same as yn plus 1. So here's the dense output, and the expression of the coefficient bi is the following, and we can have this polynomial expressed as the following, and you can also take a time derivative to have the expression of y prime by using this polynomial. And then with this y prime, then you can prepare the capital Y's. Then you can continue your RK step at the Mesh Refinement boundary. So again, to be more specific, again, so here I show the grade, a typical Mesh Refinement grade. So again, left will be the course level, and right will be fine level. Again, fine will take 2 complete time steps in order to match to the course level. And we call this, so instead of add 4 times of goal zones, right? In the new method, we only need 1 goal zones. So it will be the same size of the inter-process boundary that you only have 1 goal zone. And again, then we call the course level L-1, level L-1, and the final level will be level L. And first, we do a complete RK step at the course level. Then we will have all this Yn and Ki, which correspond to the course level. Then with that, we can create a polynomial you can evaluate anywhere in between both Yn and those Y primes. Then we use that information to fill in the Y's in the circles. So first, we do a prolongation of this Yn and the Ki's and the K's to the goals point. Then in all these goals point, you will have access to the polynomial basically. Then after that, using this expression, because you have this dense output, but you can create a dense output based on this Yn and the K's. Then you can use this dense output to represent this Yn and Y prime, and in order to represent the intermediate stage Y's. So then this blue part will be the Taylor expansion around the initial stage. The blue part will be the Taylor expansion around this intermediate time slice of the fine level. So we can set this theta. So theta equals 0 correspond to the initial step of the course type part of view, and the theta equals 1/2 will correspond to the intermediate time step. First, yeah. Then with this case, with this capital intermediate stage Y's, we can evaluate, because you only, because this F will contain the finite difference operator, and because we already have actual goals point, we can have a valid case at a boundary between course and the final level. Then we can use this case to have valid interior valid function value of the interior point. Then again, we do restriction from the fine to coarse. So here's a comparison between the 2 methods, the CarpetX and the CarpetX. The black point will represent the interior point, and the circles represent the buffer zones or goal zones. As you can see, that the buffer zone will be 4 times larger for the CarpetX method, CarpetX subcycling implementation compared to the CarpetX version. And we also need to evolve the buffer zone for the CarpetX version, but we don't need to evolve the goal zones of the CarpetX version. So with that, we implement that the new subcycling in CarpetX. Then first we do some tests to make sure that our implementation is correct. So the first case we have tried is a scalar wave. So at the beginning, you will have a Gaussian pulse, which centered at the origin, and where the evolves is probably outside. And we have a box in box. We only have 2 levels of refinement, and the refinement boundary will be at x equals 1 or r equals 1. And here's a snapshot at t equals 1. So basically, the Gaussian pulse propagate right across the refinement boundary. And here we show the difference between the numerical solution and the analytical solution of this linear wave. And so the upper panel will be the uniform time stepping, and the lower panel will be the subcycling version of the same setup. And so different colors. So the black will be the lowest resolution case. The orange will be the median resolution, and the blue will be the hazard resolution case. So as you can see, we increase the numerical error decrease. And if we rescale the median and high, assuming first order convergence, that they match pretty well, and which suggests that the whole implementation is first order convergent. So both, as you can see, that both the subcycling and non-subcycling case have very similar behavior, very similar convergence behavior. They are both first order convergent. So that's the first test we have done. Next, we want to try BBH simulation and using much more levels of environment instead of 2. So before that, we need to implement space-time evolution code or SOM. So in order to do that, we use this a code generator called Generado, which is based on Mathematica and also this very nice XAct package. And Generado now support not only CarpetX, also support Carpet and Mesh and also DangerGR. And we use this new code generator to generate C4 which basically the C4C formulation of Einstein equation. We also regenerate the wild scalar calculation such that it's native. It can it's native GPU friendly. So here's just give you a sense about how this code generator looks like. So so here's an example of the momentum constraint calculation from the ATM variables. So here's the equation looks like. Then in the Mathematica, then what you wrote is just write the left-hand side and comma and right-hand side expressions. You can see that we use then because of using XAct, we're using the convention that they are using the without minus will be the up indices, and with the minus will be the down indices. That will be the expression you need in order to then the generator will generate the corresponding C code that you want. Okay, then doing that, we implement we turn on the subcycling for the C4 cow SOM and did a typical BBH simulation, which is Q1 non-spinning case, and I think it have. Sorry, I don't remember how many levels they have. Anyway, then here is the 2-2 mode of the Psi4 And here we show T equals between 300 and 600 M. And again, the different color represent a different resolution, and they match pretty well. And we also compare the difference between the different resolutions. So in the bottom panel, the black line represents the difference between the low and the high resolution, and the orange will be the difference between the medium and high resolution case. And again, the blue one will be the same with the orange one, but rescaled, assuming that it's first order convergent. And as you can see, after this rescaling, that it matches with the black line pretty well, which means that our whole implementation is first order convergent. Again, so that's just self-convergence test. We also want to make sure that there's no other errors. So we also compare our waveforms to these to the LazEv code. So as you can see, they match very well, and the relative difference, I think, is less than 0.1% in both the amplitude and the phase. Okay, then because of a different implementation of the subcycling, we also expect that we can have better scaling performance compared to the CarpetX subcycling case. So here we show the strong scaling for the previous EBH simulation, and the axis will be the number of nodes that will be used for the scaling test, and the y-axis will be the speed and per day, for example. And the different color represent different setup. So the orange one will be the old CarpetX and subcycling, and it's running on CPU. And the blue one will be the new CarpetX implementation, also running on CPU. As you can see, the new subcycling implementation, and not only is faster, it's also scale a little better compared to the CarpetX version of subcycling. And the black one will be the same CarpetX subcycling implementation, but running on GPUs. So instead, so by running that on GPU, you can have another 15 times speed up for the new CarpetX version of subcycling implementation. So here's the weak scaling of the same comparison. And as you can see, they have similar weak scaling in both CarpetX and CarpetX, and also CarpetX CPU and CarpetX GPU. So they will they all have around 80% efficiency for the 64 nodes case. Yeah, just a conclusion that we have implemented a new subcycling algorithm within the new CarpetX driver, and it is first order convergent compared to the older CarpetX, which is second order convergent. And the new subcycling implementation both improves speed and scaling performance on CPUs, and it's also GPU friendly. Okay, do we have any questions before I go into the next part?
Okay, give me a moment. Also, quick question. Everyone online, can you... Oh yeah, Roland, I saw your comment. Can you hear us again?
Yeah.
Yes, I can hear you.
Okay, very good. Do we have any questions? Zach in the room, let me just hand over the microphone.
Hey, Liwei.
Hi.
Can you hear me okay?
Yeah.
Okay. Yeah. Yeah. Great talk. So far. Right. So yeah. A question. Have you discussed with Lucas anything about how this is going to scale once we add the multi-patch for the wave zone?
Oh,
Any predictions on how those curves are going to be adjusted?
I think there will be not too much effect because I guess that for the multi-patch, for the other patches, instead of center one, there will be one level, right? And it will be the closest level, I guess.
Right. I think
So,
so.
yeah,
You
that
also have the advantage that you just naturally get on all those coarse levels going all the way to the outer boundary. So I don't know. I could see things getting better or worse. Maybe about the same.
okay, then I don't know.
So Helvi asked if I have any guess. Not really. I think, like Zach said, things can get either better or worse, considering that, the whole point of a multi-patch system is that you have as tiny as possible of a Cartesian grid in the center, and then you just extend your wave zone as far out as you can. Maybe that will dominate on timing, but I I really try not to do those timing predictions like this because it's very hard to human predict what's going to happen in that, so I just don't know.
Okay, very good. Roland, I see you have your hand up. Please just unmute yourself and ask your question.
Okay, thank you. I actually have two questions, a nice one and a mean one. I'll start with the mean one. In the slide that you're showing me just now, you show me reasonably nice scaling for the CPU part of CarpetX. No, next slide. And then you have the GPU scaling, and the GPU is faster, but the scaling isn't really great. At 64, yes. You're no longer getting any speed up. At which point do you reach, say, 80% scaling efficiency? If you know.
Oh, yeah, I think I know. Let me check the number. 80, you say?
Roughly, right?
80 for the GPU.
Yeah.
8 nominal. Basically, you don't have enough work for the GPU for this many of nodes. So 8 will be 70 already for the GPU case.
Okay.
70%.
Does it get any better if you improve how you lay out the grid in memory, given that the GPU is very sensitive? Or
what do you mean? What do you mean? Layout?
Making sure that the grid size fits the GPUs exactly.
Oh yeah. That this plot is from that setup. If you are not setting that, it will be like this.
Okay. Okay.
Yeah.
Okay. All right. Okay. Now for the other question. Is this vacuum or hydro runs?
Oh, this is just vacuum.
Okay. Do you have a hydro one, and do you know how this would change?
Similar. So we already so before we didn't change anything that it will scale much worse compared to this, but we update our hydro implementation such that we remove all those unnecessary prolongation, then it will have the similar scaling behavior compared to vacuum.
Okay, thanks.
Okay, very good. Do we have any more questions? Not in the room, and I'm also not seeing anything online. And Liwei, I understood that was kind of part of your talk, right? You have another 15 minutes to until we have to finish.
Okay. Okay, yeah? Great.
Very good. You stopped sharing? Was that on purpose?
Yes.
Okay, very good.
Okay. So next, I want to talk a little bit about how to modify your own CarpetX SOM such that you can use the new subcycling feature. So
Okay.
let me share this in
Oh yeah,
chat.
exactly. Yeah, can you share the link also in the back? Can you see the font size? Are you okay with that, or do you need this a bit bigger?
Oh,
Okay, yeah. So could
is
you
that good
please
enough?
maybe a little bit more? Can you
Okay.
just? Okay, how's that? Yeah, nodding in the room. Everyone looks happy.
Okay.
Very
Thank you.
good. Thank
Thank
you.
you. Okay. So in order to use the subcycling, first you need to use a different repo, a different fork of the. We are trying to merge the to the main branch of the CarpetX, but right now, yeah, right now it exists on different fork, and the branch name will be definement of that fork. And after that, you will add 2 more parameters in your path file in order to own the subcycling. Will be the use subcycling working process equal to yes, and you need to turn off the restrict during sync. So that's the first thing. The next thing, in order to modify your own SOL to use subcycling, the first thing you need to do is to add a lot more grid functions. So suppose in your SOM, you already have a right-hand side grid function. We store the right-hand side calculation of your simulation. Then you will need add 5 more using this exactly name underscore odd underscore K1, K2, K3, and K4. That's the, for now, that's the, that you have to modify the interface. So for example, in say for C, the subcycling version, before you have this underscore right-hand side, then you will copy them and modify right-hand side to the old in K1, K2, K3, K4. So that's the step 1. Then step 2. So basically you need to remove all the things in your schedule, and for the evolution variable, the subcycling version of the driver will take care of the things for the evolution variable automatically, but other than that, you might still need to think in your current implementation, but you need to remove all these things and using loop all device, which then rebuild all the intermediate variable from the evolution variable. That's the that will be that require the more careful thinking about your SOM. But for the vacuum case, I think we only think the average variable. So for the vacuum case, you don't have think of non-evolution variables, then you don't need to modify anything. So for the first, after you've done the step 1 and step 2, then you can do your simulation with the subcycling. And the step 3 will be that if you want to have a more efficient, which remove all the unnecessary things of your unnecessary prolongation operators in your implementation. Then you need to schedule all the routines from the ODE solver post step. You need to schedule into a new time being called ODE solvers post sub step, and remove all the things of the evolution variable, because the subcycling version of the driver will do that automatic for you. Then after that, in the parameter file, you will add another option which that do not using the post step for during the arcade substep using this type instead. Then after that, you will have more efficient subcycling evolution of your song. Yeah, that's all you need to do in order to using subcycling. If you already have a working CarpetX song, then here's a list of the songs which already be modified that's compatible with subcycling. And for the space-time, that it's also on my fork, and we have different versions of the C4C implementation. And the C4C is a very minimum modification that we mentioned before of the original C4C song existed in the main branch. And for the aspects that we also have also on my fork, and that I already made a modification of all the 3 steps such that it have efficient subcycling evolution. So we also have a new version of the Y-scalar calculation. Yeah, just okay, Steve Raffin. Okay, I think that's it for the introduction of how to use the subcycling. Yeah, I will stop here. Thanks.
That was great. Thank you so much, Liwei. Do we have questions either here in the room or online? I don't see anything. I actually have a question for you, Liwei, because you have your songs here, right? And they are code generated.
Yeah.
Do you have
Yeah.
the original Mathematica notebook also available if people want to look at that version?
Yes, it's all in the song. So
Oh, it's all
it will
in there. Oh,
be,
fantastic. Yeah.
there will be a warframe, and
Mhm.
that's all the files that, so this file will generate this file, this file will generate this file. Yeah, that's all in there. And you can also have a peek about the equation. This is coming from the Mathematica, and you can check easily with the abstract indices. Yeah.
Nice.
Yeah.
Yeah. And then I guess another question similar to what Zach asked before. Have you or do you have any plans to say work or talk with Lucas on comparing the different implementations for
Yeah.
the space-time evolution? Because we now, so we have
Yeah.
your code, we have Canuda, we have, and I don't remember the name. Lucas has to help me out.
The name of the new DSSN code is Cardamouth DSSN, but
Cardamouth.
it's called a big package.
Yeah. So Cardamouth, I think would be really interesting to see that performance comparison for all 3 of them.
Yeah. I'm interested, yes.
Yeah, no, this is really great. Okay. Do we have any other questions or comments? Okay, not in the room. I also don't see anyone else online. Then let's thank Liwei again.
Thanks.
Thank you so much. Okay, and let's hand over to the next speaker, which is Jay. Oh, shouldn't we continue? Oh,